Let me start by giving sort of a brief outline of the tutorials. So the first part, it is divided into 6 parts, labeled 1, 2, and 3, and each of them have a part A and a part B. And so first I will give some general motivation for information theory. It's really not needed for half of you, because, but I will talk about information in general. Then I will get to something called relay network solvability and equational logic, and that is something that I think will be new for you, and it's actually quite cool and interesting because it involves also automated theorem provers. So sort of the highlight for that part will be I will demonstrate some automated theorem prover that can give all sort of interesting answers to simple questions involving sending messages through networks or things like that. I will do a graph-free approach to communication networks, also nice. So actually, instead of having all these graphs, you can actually just feed in, you don't have to feed in pictures in the theorem prover, you just feed in equations, and then it gives you your answers, or at least can work on your problems. And then I will prove, which is also new, I haven't presented that anywhere, but it's actually not that difficult an argument when you set up the right machinery. I will prove that the solvability problem for relay networks is algorithmically undecidable. So this is, maybe I can just say a few seconds what this is about, but it basically is saying that if for people who know about network coding, relay networks is networks, like a network coding, but where you can require that different nodes are applying the same coding function. So there are some constraints on what you're allowed to do, but otherwise it's the same setup. And it turns out that is undecidable, that type of problems, and it's actually a fairly straightforward reduction to some other problem, but when you have set up the machinery. Then in part 2a, I will talk about these graph guessing numbers I also spoke about in Hong Kong, and but I will link them up to causal networks also. And the highlights here, I would say, is is examples of graphs where of course I will give you the definitions later, but it will be some graphs that is directly illustrate some shortcomings of Shannon's information inequalities. So in order to give good upper bounds, I need to, so to speak, use non-Shannon information inequalities. And there are interesting open questions related to that problem. Then in part 2b, I will talk about something called term coding, which is also new. It's a kind of generalization of the guessing games, but it also unifies a lot of other things. So the highlight would be that network coding solvability, the hat graph guessing games, and index coding all fall naturally into that formalism. And again, it's something that is kind of graph-free, so it's more about looking at certain type of equations, and again, things you can do in equational logic, but it also leads to a new type of problem. It's really a new type of problem. So people who do equational logic and automated theorem provers is not exactly what the provers are dealing with. It's a slightly different type of problems. And then, so this is really, there's a new class of research problem linking to information theory and finite model theory and equational logic. And this is really very cool, and I really hope that some of you will work on this, because I cannot single-handedly, together with a few students, there are so many questions you can ask and so many things to develop, you know. So I think you all know the feeling. And then I will prove something that is also kind of cool. Again, it drops out of the theory quite fairly easily, but it's quite, maybe a curiosity, quite interesting, that if you have a general and network coding problem, you might ask, can you actually do with just one coding function? And it turns out that there are some caveats, you know, I have to specify exactly what I mean by most solvable networks, but it turns out in general, if you write down a general communication networks, if it's not degenerated in a very specific sense I will define, then you can actually just do with one coding function. However, you cannot achieve the full capacity. You cannot, so if you have solvability, the general coding function, then you can use one coding function and achieve sort of the information theoretic limit. You know, in the limit you can you can solve it, so to speak. From an information theoretic or practical point of view, you can solve it with just using one coding function. And again, it's something that pops out of the general theory fairly easily when you set up the right way of looking at it. Then in part 3a, I will do linear network coding over rings and modules, and that is also new for many of them. Of course, some of it has been published or things like that, but recently, I haven't talked about it before really. And the highlight here is that it's a general theory that makes it possible to talk about transmission of infinite states. And it turns out that something called Dedekind finite rings play a very important role in this theory, for some reasons I will explain. And again, it's linked to equational logic and theorem proving. So, and finally, I will talk about dispersion. That was a topic I talked a bit about in Hong Kong. I think I gave a lecture there outside the program on dispersion. And again, here I will do some demonstration with a C program. And actually, to make this talk a bit more accessible or more hands-on, some of the things I illustrate, I simply illustrate either by a theorem prover or by some other software that can sort of illustrate what's going on. So it should be. Now, let me just give a very short motivation for this. So information theory, this is just a general motivation for our field, or for actually, I mean, information theory is really a rich topic with many different branches. It's many open questions, which of course are very attractive to work in, and also it has had a very strong impact on as a design driver for technology. And in general, also, information theory is about fundamental limits. So, when I had to explain to my colleagues at my work what information theory is about, you have to explain about impact and how important it is. And here is an example to justify your existence in a modern university. You have to explain that what you're doing actually have impact. And here I found, like, literally speaking, hundreds of different research areas with their own more or less obscure names, commerce informatics, communication informatics, computational arts and creativity, and you have lots of different dental information theory, but these are actually fields that have conferences and meet up or things like that. So it's.
What is coastal informatics?
Well, don't start to ask. Get started. So you ask what is coastal informatics? I mean, I certainly wouldn't know half of these areas, but. I think it just shows we can be a bit proud of ourselves, I think, because obviously we are kind of the top of the food chain in all this, because, I mean, I'm not sure, you can probably only a small fraction of these areas are dealing with even Shannon's information inequalities, I suppose, or I don't know actually, probably many of them are, but you can, so to speak, probably classify the different areas according to which theorems they're using. And if you look at which areas are using non-Shannon information inequalities, I'm sure it dropped from many hundreds areas to probably less than a few, I mean, at the moment, but maybe that will change. So, information theory, well, what can we say? If you have a memory stick here, it's full, you might ask how much information is stored on the disk. And this is, the wrong answer is that it's 64 gigabyte of information. That's not the correct answer, of course. But, of course, it contains 64 gigabyte of data. But the point is, data is not the same as information, obviously. So you can have two different memory sticks here, and they might, both of them are full. But the point is that maybe both of these full files or complete files contain the same data. They might contain the same movie file, for example. Same movie, not the same file, of course, but the same movie. So it's the same information they contain, but so really you need to take data compression into account when you measure information. That's a fundamental thing. And so sort of, again, very briefly, you can say information theory is a measure of amount of information. It's measured in bits. And you could say informally a measure is sort of a measure for your lack of surprise you get, when you find something out. Or so this is a definition you all know. And we have Shannon's famous formula here, but that's the formula you often discuss if you meet other mathematicians outside information theory. You find yourself discussing this kind of equation. Information theory, look at this equation, is ugly. Where does it come from? Or people have all sort of objections to it, because it looks at first ad hoc, but of course it's a very fundamental definition, and there are many different ways you can sort of justify it. But basically, one way of looking at it is that you simply have some information, you want to store some random element from some big set here. It could be some data file or something. You want to store it, and the question is simply how much. What if you store it and you have some probabilities distribution on your different movie files or your different files? What's the most effective way to store it? And the average length of this code effectiveness of that storage or that code is simply essentially the entropy. So then I will just briefly go over. We have maximal entropy principle. This is given some probability vector, given some constraints, maybe in the probability, maximize the entropy. And there is a philosophical point here that is really a minefield. It's something I don't want to go into. It's the kind of thing that you can discuss for hours and people can write many papers about. But somehow I'm a bit so you can already don't object to what I'm saying now in some sense, because I know it's complicated. But you can say in some sense the philosophical point of assuming maximal entropy is in some sense we don't want to assign knowledge we don't have. We simply assume we have. We don't want to pretend we have greater knowledge than we actually have. So to give an example, if for example we know that a variable x can take these n values, they are different. So suppose they are different values, and they are given. So then what are the prior probabilities? You can say, somebody says, if you never heard about a dice before, but you know there are 6 outcomes, the question is what can we assume about the prior probabilities of the different sides? And of course you can see this is a minefield because, but the point is that in some sense the problem is that if you assume each of the outcome have exactly 1/6 probability, if you have six outcomes, then nobody can accuse you at least of sort of pretending to have some extra knowledge, in the sense that you sort of start to, if you give one higher probability than the other one, then they can start to sort of question your preference and say, why do you think that outcome 2 is more likely than 3? Then it's because you actually have some extra knowledge you are smuggling in the back door. Or here's an example: you might have n values. In this case, you might know that the expected value is given by E, and then again you can try to work out what's the prior probability. So I've just mentioned this important tool. I don't want to go into, but Lagrange multipliers is of course a very important tool for these kind of things. And for the 2 examples, I will just point out that in one case, if you actually try to maximize the entropy, you actually get the symmetric distribution in the first case, and in the second case, you get distribution like this. So for example, if you have a population and you know nothing about it except you know the average income people have or something like that, or maybe how are the income distributed? Well, then we can see from this solution essentially there are 2 possibilities, that there are two possibilities. There are lots of poor people and few rich people. If depending, of course, on how many people you have, and this is a very poor model also. But also it could be there are a lot of rich people and very few poor people. There are sort of different solutions you have. They all maximize the entropy depending on the relationship between E and how big these incomes are compared to the expected ones. The reason I mention all this thing about maximal entropy is that one of the results I will present in the tutorials is actually where we apply the maximal entropy principle to communication networks. And what is remarkable is that, well, you can think about a network like that, like a physical system, where each of these nodes represents some kind of physical state, and the diagram illustrates sort of causal relationship. So, for example, if there's an arrow from node 3 to node 1, what it means is that the state of node 1 is determined by the state of node 3. In this case, you can see the state of node 5 is somehow, in this case, is actually determined by itself. That means actually in that formalism, that is kind of a random. It's just a function of itself. That means that it can be any value. We don't know anything about it, really. But you have node 2, on the other hand, can be determined just from knowing the state of node 1. So in this physical system, where each node is determined by the state of its predecessors, and if you assume it's some kind of in a stable situation, you know that it's a stationary situation, you might ask, and each of those it's governed by local laws we don't even know. We don't know the local physical laws, but suppose we just apply the principle of maximal entropy. Then we can ask, what is the uncertainty about the system? We can ask various things about the system, and now comes a remarkable thing, and that is that if you actually apply that to a communication network, so if you have what, for example, it will be more clear later, after this machinery are developed, you will understand it more clearly, but you see if you have like a communication network like here, I will actually give you the more details on it later, but the point is that this corresponds to this kind of causal network, if you want, and it turns out that if these states here are determined in such a way that the entropy is being maximized, it turns out that this coding function, these natural laws you have here, if they maximize the entropy, that happens if and only if the coding functions solve this problem essentially. I mean, there's a decoding going on here, so I haven't mentioned, but I'll come back to that. So this is the first slide. So now I might have to speed up a bit, just a moment. Now it's getting more fun, I think. So in this, I already told you that I'm going to introduce this kind of formalism and look at it as a part of equational logic. So this is again something you all know, kind of really basic example, but this is an example of what kind of problems people look at in, say, network coding. We have a satellite problem, and we are beaming messages up to the satellite. But the point is we can actually write down the problem, which is, okay, so let me explain. So we have a message X from an alphabet, from some big set is being picked from east to west, and we have a message from Y that is being sent from west to east. And the point is that if the satellite then computes some kind of function or some value from the alphabet, computed from X and Y. But you can actually write down what is the requirement here, that is that of the coding function, that is that there is a G that is like a decoding function. So that we have this equation, and there's an H that we have this equation. And this I will skip, but okay, so I think I will skip this. This just shows, give examples of solutions. You will see that actually there is a solution if and only if F define a Latin square. That's not a big surprise. Let me just make it sure. When I talk about network coding in general, I normally represent it like this, like all the coding functions are sitting in nodes. I think about it like a circuit actually. But often in the literature of network coding, people like sometimes to put the functions on the edges. But I put them definitely on the nodes, but they're completely equivalent. You can take such a problem and just put nodes where every time you have a function symbol and link it up like that. So this will be my representation. I always assume, just for presentational purposes, that we work over the same alphabet everywhere. So it's not like we have different weights here and different bandwidths. We just assume one fixed alphabet that we look at. It makes it more clean, the general theory. So this problem, of course, is the same as the satellite problem. So the task is to solve these term equations, and you can say we want to find a finite alphabet and choose a coding function f, g, and h that satisfy these equations. That's really what it means to solve the satellite communication problem. But of course, if you speak to somebody in equational logic, what they will say is that you will say, well, we have to find a finite model A where the equations hold. That's really what it's about. That's just a different community. That's how they will speak about it. Here's another example. I will just go briefly over that, but this is also a very classic example. You know, where you have, for example, well, you have two messages, x and y, and you want to store them in 4 locations, and you want to make sure that every time you contact or visit 2 nodes, you should be able to recover x, the message x and y. And it's completely well known and easy to see that if f and g defines 2 orthogonal Latin squares, that's exactly the requirement for this coding problem. And here is an example of how it could be solved. But now let's look at it from in regards to term equations. So here we can simply write down with the decoding function and so on, and this is the term equations we need to satisfy. We need to in order to solve that distributed storage problem. Does it make sense, or any questions? It should be fairly easy. So network solvability over a fixed finite alphabet can simply be stated as about the existence of a model that satisfies a list of equations, term equations. That's of course simple observation. And in general, if you have a network coding solvability problem with k receivers, that's equivalent to some solvability of some term equations of this form. It's a special form because when we actually look at solvability problem, we require that one of the receivers receive one of the original messages. So the variables in these terms, they correspond to messages we are sending. And the terms is like what you receive in a node, exactly like in these examples I showed before. So in our case, we look at these kind of equations when we look at network coding. Sorry, T represent terms, T1 to Tk. Is what your question, what does T represent? Or? Yes, these are terms, so this would actually, I think I'm sort of, I will, in a few slides, I will actually be a bit more specific about equational logic, but you will see also for some examples when I run the software, you can see what it is about. But it's essentially, these are, instead of, this is an example of a term you have here. It's just a shorthand notation for a term. These are variables. I will come back to that. Just bear with me. But a relay network is a communication network. It's defined as a network coding, but different node might require to use the same coding function. Or you can say off-the-shelf coding. You know, so you have different nodes might have to use the same coding function. And I will give a motivation for that also. Why this is so important? Actually, these kind of things. It's not just that you can use the same coding function, but it's also related to dynamic networks where you have link failures and lots of other things. But okay, so for example, if you look at the butterfly network problem, you can. What if we want to decode with the same function as we encode with? So now we have these equations. Now I just use the same function. I'm saying I just want to use one function f, and let's try to solve that. And then now I'm going to use the software. So this prover, maybe I should say a bit about the software I'm using here. I'm using prover because it's actually kind of a bit out of date. It's not being updated anymore, and it's but it's very nice for these kind of things, and it's freely available and so on. Of course, normally any serious theorem prover today, a person will probably use COC and some other system, but for this lecture I will use prover because it is a quite neat system. And it is shipped together with maze that finds finite models and counterexamples. So let me see if I can run it. I actually wanted to run it originally on my screen, so I just would go out on my PowerPoint and do it. However, there is a problem with the font. It's not, on my Mac at least, I had some problems with this font. It's very small, so I decided that to embed it in the PowerPoint. So you can see what I'm doing here is that I'm actually trying, this was just this simple butterfly network problem where we just want to use the same coding and decoding function. I want to understand, for example, what am I doing now? So I want to see, for example, oh, I shouldn't have this here. I was proving something here. What did I prove? I think I wanted to prove that it must be commutative, I think. No, wait a minute, that was, yes. I think I proved, this is a proof that it's commutative. No, wait a minute. No. No, I was just proving this, that I was proving this characterization. What is the exact characterization of f satisfying this coding and decoding function? Which functions is it? And exactly the one I talked about has to be commutative, and it's a kind of a binary system. You just have a bracket. So okay, so what I'm doing now is I want to see how many, if your alphabet of size 6, how many non-isomorphic structures satisfy that, and you can just to get an idea of the speed, it comes very fast also for much larger alphabets. This was just an example. So if you have this coding function f in the term equations from before, you have, these are different examples of solutions. So these functions, you can ask how many there are, what kind of, how to characterize them.
So what is the smallest alphabet size?
Sorry?
What is the smallest alphabet size?
The smallest alphabet size, that is, for this one actually you can do 2 because you can just do the exclusive OR of x and y actually for this one, but that is, so now let me jump to the next one. Because now it's a bit more interesting, because when you notice when we have these coding and decoding functions, there is no reason why we should so to speak, put the argument in a certain order. We could, for example, have put the terms equation like this. It's the same function f you're using. You're asking for a function, but you just say, when the function decodes, it picks as the first argument x, and as the second argument, it picks this value here. Actually, this one doesn't even correspond to the butterfly network, I can see, because this one is probably, this is a different message from this one. But you can write down term equations, and then you can solve them. Let me go to this problem. So now we look at this was a storage problem before, where we have 6 different variables. You might ask, can this be solved by 2 coding functions? So here so one way of encoding would be like something like that. Actually, maybe not the same problem, but I'm actually, it's not exactly the same problem I can see, but suppose we look at these term equations and then I just want to illustrate the software. So let me illustrate what it's doing. So here we have our equations. Of course, it's not really the storage problem I can see, because here we have f of x, y, and here we have f of x, y. So it's a different message, but we have, the point is that for this problem there turns out to be different encoding sizes. Let me just show the software. So we have these equations, and the nice thing about it is that it can, it's just to illustrate what kind of, so here I can put the size, I want to do a search now, let's say domain size, and I put, and this is freely available, by the way. It takes 2 minutes to download, and it's very simple. And you're simply looking for models, and you find there's one model of size 4 where we have these coding functions. And so forth, and we can also look at now another interesting feature. We can look at how many non-isomorphic solutions you have and so on. You can maybe I shouldn't go through that, but you can see for 5, I think there's also only one model and so on. But you can play around with these things, and now you can ask yourself, maybe this distributed storage problem can actually be solved with just 2 coding functions. The equations I wrote up was not quite a solution to them because there was some fiddling around. But one can play around with the system and see what they can do and what they cannot do and so on. So this is what it's about. So briefly, one explanation why, let me see, did I not jump a slide here? No, yes, here. So one, you might ask, why do we require the same node to have different, to have the same coding function? And one way of explaining it is that we have, often what happens in a communication problem is that, you might have link failure, you might have the topology of the whole network might change. And then it might be that certain nodes are simply ignorant about what happens later when they send it. But one way of modeling that is we simply say, well, there is a set of possible worlds we could live in, a bit like Kripke's puzzle of world semantic as known from logic. So we have a number of different situations we could be in. And then some of these are coding functions, some of the nodes, so to speak, live in different universes. So this world is just a situation that might be the case. Maybe, and this is a different situation, but some of the nodes, maybe in the beginning of the network here, is the same across the different worlds, but some of them might be different. So when you choose your coding functions, you want to discuss how effective various coding functions are, you have to look about the expected amount of data you can send through the network across all the different possible worlds. You might have a probability distribution on the different worlds and so forth.
So the world is just described by which links are present?
Yes, a world, I mean, of course it's a lot of freedom, but you can think about a world is like you might have in world 1, these are the links available, exactly what links are available. But more than that, because it could be that these two worlds also overlap in some parts, that means they have knowledge of each other. It's in some sense the action of the different nodes here, there's no difference. If this node is using a certain coding function, this one is using the same coding function because it doesn't know which of the two worlds it belongs to. So you can see here we have you can also sort of, this very flexible notation, you can actually take these different worlds, but you can also put them into one sort of diagram like here and have like the world sort of splits. You might split, for example, in the sense that in one branch, in one world here, the coding function here is sitting here, but the same coding function is sitting in this world, is sitting in a situation where there is a link failure here. Okay? So this is simply a setup, relay networks is a setup to discuss these kind of problems. So equational logic, I think it's kind of intuitive what it is about, but it's basically a language consists of a set of function symbols and constants. We don't really have constants here, by the way, when we set up problems, obviously, because we don't. Maybe one constant, like 0, like sending either nothing or some default symbol, but in general, we don't really use constants. And then we have a set of variables that representing the different messages being sent. And then for each function symbol, it has a certain arity that depends how many argument it takes. That's what's for the syntax, and then the semantics is simply a set on which each of the function symbols are interpreted as functions on the set. So if you have a binary function symbol, then as a syntactic object, f is just simply, you can say a two placeholder like this is just a syntactic object, or sometimes people can put a bar on top of this to illustrate this is as interpretation of that function symbol, which is a map from like this, where A is a universe. So that's also what I write here. An interpretation of a language is basically an assignment where each function symbol is assigned to basically to each to a function, and each constant symbol is just an element denote an element in the universe. So here's an example of a model. So if you, for example, have this term equation or this equation here, that's the same as, you can also write it like this. The models for this equation is exactly semigroups on A. Of course, they don't have to be finite. So in general, for equational logic, we also look at infinite models. Yes?
Is it different from the compound set? Because
from the
network, there is a setting called compound set.
From what?
Compound. So the name of it is, there is a state for the network. Okay, so it means that all the links, there is underlying random variable called the state. And the nodes are not aware of the state.
Are you talking about what?
So when you have dynamics, so there are several networks that are possible.
Yes, yes.
You can visualize it as there is a state, which is a random variable, which tells you which state is the current, setting of the network. And you have this random variable just S. All the network, receive signals, links, etc. Function of S.
Yeah, normally I like to. Sorry, I simply don't understand. I'm a bit. Maybe it's early in the morning. I don't quite understand your question. I'm not sure I can paraphrase your question, but it's somehow. I hope it should be clear from here. I mean, about what a dynamic network is. I mean, I don't think. But maybe we can talk about it afterwards. Then, if I understand your question in the break, then I can address it after the break. Okay, so there is a simple gadget now that allows us to because now I'm going to show undecidability and I'm going to show various things. We can have a simple gadget that consists of these three equations. If you don't like three-area function symbols, you can also do gadgets with two-area function symbols and so on. But this is the simplest way of constructing it. What it's actually doing is like taking the minority value. So what it's doing is that if you take three inputs, three arguments, and the two first ones are the same, and the third one might be different, then it always plug out that value. And you can also have this one here plugs out the middle value, and here the first value. So you see, this is really just like a minority function. You simply do a vote. It looks at the received values, and then it selects the one that occurs the least. Now this, of course, can be simply written down. We can write down a relay network with this communication problem. If you don't like that it's the same message being received, you can typically just rename the variable. So you can have, these can be one set of variables, these can be different variables, these can be different variables. If you want your relay network, you don't like that some of the messages never are received anywhere, you can just make an extra link from X to some other place and so on. So you can do any kind of network you want. You can also have a multiple unicast network, or you can do a little network, but it essentially functions as that gadget. So it forces that coding function to behave exactly like this. But now it's clear that if we have two terms, S and T, then it turns out that this one, if for all sets this one holds, that happens if and only if the two terms S and T are equal. If you don't believe me, actually, I can verify it here by prover. I don't know if you want to see that proof. It is a bit maybe waste of time, but I have it. You can actually. It's an absolutely trivial argument, but you can actually. I think it takes a few. I don't want to be late. I think it's more important. We get to the undecidability. So we also want to have constants in our language. Constant, because we really just have functions and coding functions. But you can also easily, by use of this gadget, you can easily force a coding function to behave like a constant. So what you can do is you can just simply put an expression like that. You can always relabel the variables if you don't like that variable to occur elsewhere. You can, so to speak, and you can add some extra stuff to the network again, so it become a special type of network, like a multiple unicast network or something like that. But the basic idea is that we can force certain functions to behave like constants.
Okay. Just why don't you simply write that fx equals to fy? This would be shorter to write it.
Yeah, but if I write, yes. So the question was, why don't I just write fx equals fy? Yeah. That, of course, you're right. The problem is that I'm doing it in a setting where we want it to be implemented like a relay network. And if you do f of x equals f of y, we cannot require that. You see, that's why. It's not, as far as the term equations are concerned, of course we could do that. So now, why is it undecidable? Now it's actually very, very simple to see, because it's undecidable in general to determine if a given system of term equations has a solution in some finite model. This is a standard undecidability problem. But now if we are given term equations here, then if it has a solution in a finite model, then it happens if and only if such a system has a solution. Very simple. And of course what you notice is that it's actually undecidable because we can arrange it so it's just one message being received, namely Z. We're only concerned about that message. In some sense, all the other variables just serve as noise variables. They're just noise that's sort of a bit controlled, in the sense that they're all the same noise from the source or something. But so it's actually undecidable whether there exists a finite alphabet and encoded functions that ensure that a single message X is received correctly at all the destinations. So, and of course you can modify this very flexible notation to set up. It's very easy to use also the gadget and other things to show that you have solvability for multiple unicast networks. That means that you have n messages being sent to n receivers, each message to one receiver. So, so this is what I write here, again, because the network solvability problem can simply, this one is undecidable, but this can be reduced to a unicast problem if you want, just by transformation. So that's undecidable. So that was the end of, I think, this part. So any questions or? But I hope you will agree when you set it up like that. It's very simple. I mean, to see why it's undecidable, but also it's very interesting because it means that you can, for example, if you take your favorite algebraic structures or some special rings or whatever, you can immediately write down relay networks that exactly are solvable over alphabet where the coding functions satisfy these conditions, your favorite conditions. Then you have some extra functions, you can typically don't have to be concerned about. If you count, for example, how many solutions you have to your network coding problem, it's exactly the same number of solutions you will have if you disregard these extra functions you use for auxiliary functions, if you disregard them, and then so it's exactly the same number of solutions. You have the same problem in disguise in some sense you're looking at. So should we have a break now? Or? Thank you.